morning children and welcome back to physics class again. So today we are going to start with the second chapter, that is units and measurements. Alright, so we are dealing with different types of units and measurements. Now, before I start what is unit and what is measurement, some of the basic thing that we need to know is what do you mean by quantity, right? Quantity is something that you can measure. Correct? Quantity is a measurable value. Something that you all can measure is called as quantity. Something that can be measured like mass can be measured, length can be measured, distance can be measured, time can be measured. Some quantity that can be measured is called as a physical quantity. Now, what do you mean by a physical quantity? Physical quantity is a quantity where you can measure it and wherein the quantities where physical laws are applied to it. Okay, so laws of physics are applied to quantities. Those quantities are called as physical quantities. Alright, so physical quantities are divided into two major quantities. One is called as the fundamental or base quantity, and then we have something called as derived quantity. So what are these fundamental and derived quantities? Fundamental quantities are the quantities which are independent quantities. Okay, they do not depend on the other quantities. They cannot be disintegrated further. Alright, they are independent. Like mass is an independent quantity. Weight is nothing but mass and the gravitational pull. So weight is nothing but it has mass and it has gravity. So therefore we can't call weight as a fundamental unity. But mass is mass. It is independent no matter whatever the condition is. So that is a fundamental quantity. But what are derived quantities? Derived quantities are the quantities which are derived from the fundamental quantities. Alright, like what? Now suppose we all know what is speed, right? Speed is equal to what? Distance divided by time, right? Distance is a fundamental quantity and time is a fundamental quantity. Distance is nothing but what? Meter. Time is nothing but seconds. So meter per second is nothing but speed, right? So speed is derived using distance and time. So speed becomes something called as a derived quantity. Alright, so this is the difference between fundamental quantity and derived quantity. So fundamental and derived together form something called as a physical quantity. Yes, children. Now there are 7 fundamental quantities. Okay, what are fundamental quantities? They do not change. They are independent, right? Now, fundamental quantities are mass, length, time, temperature, luminous intensity, electric current, and amount of substance. So these are nothing but they are called as fundamental quantities. Now what is all of these? What are all of this? Let us check. When I'm talking about mass, mass is nothing but amount of matter in a substance. So let us take any matter. So how much matter that particular thing contains, that is nothing but mass. Correct? Amount of matter content in a particular object is nothing but its mass. And mass is always measured in kgs. Whenever we are talking in SI unit, we measure mass with kgs. Now, there is something called as length. The second important fundamental quantity is length. Now length is nothing but end-to-end measurement. Now if I am measuring the board, so end-to-end measurement is nothing but what? It is called as length. Okay, length or distance has infinite measurement. There's no stop. Correct? So it's an independent quantity. Now instead of measuring position of a particular object, how much it is moving, it's better I give one whole quantity to it called as length, right? So if I say measuring length is much more simpler than measuring each centimeter the object moves. So this is length is also an important quantity. Then important fundamental quantity, its unit is measured in meters in SI system. Then we have time. Now what is time? Time is nothing but it is a measurable period, okay, something that we can measure, and the unit of time is second. Then we have temperature. Now what is temperature? Temperature is nothing but how hot or cold the object is. Okay, it's better. Temperature is the unit of temperature is better than measuring how much each molecule has in itself. So the entire substance, how much it contains, that is nothing but temperature, and it is a fundamental quantity. It is an independent quantity. All right, the unit of temperature in a SI system, we call it as Kelvin scale. Next important fundamental quantity is nothing but luminous intensity. Okay, so what is luminous intensity? Luminous intensity is nothing but brightness of a beam of light in a particular direction. So how bright the light actually goes in a particular direction, how bright it is, right? So therefore its unit is nothing but candela, CD, or lumens per steradian. Then we have something called as radiant intensity. What is radiant intensity? Radiant intensity is same as luminous intensity itself, but it is measured in watts per steradian. Alright, so it is measured in what, children? It is measured in watts per steradian. Radiant intensity is a radiometric quantity. Okay? Yes. Then the next unit of fundamental quantity is electric current. So what is electric current? Electric current is now stream of electrons moving in a conductor is nothing but electric current. There is a stream of electrons that is moving in a conductor, and suppose Q is nothing but quantity of charge that is passing through a conductor in time t. Alright, so therefore we can say that the unit of temperature, or we can derive current, is nothing but Q by T. What is Q? Q is nothing but quantity of electric charge passed through that conductor in a given unit cross section. Now what is cross section? Suppose this is a conductor and the end of it is nothing but cross section. Okay, the end of it, this round thing. This is called as cross section. So therefore, we can say that current can be measured as quantity of electric charge passed in that given time interval. So that is Q divided by T. So Q by T is nothing but the current, and it is measured in amperes. Clear? Now the seventh fundamental quantity is amount of substance. Okay? Now amount of substance is nothing but the measure of elementary entality. What do you mean by elementary entality? Elementary entities are nothing but atoms, molecules, ions, electrons. The elements of different particles. Okay, so all these are called as elementary enthalpies. So the entire measure of the elementary enthalpy in a substance is called as amount of substance. And the unit that we use to measure the amount of substance present in a given substance is mole. 1 mole is equal to 6.02214076 into 10 to the power of 23. Avogadro's number is the opposite, is the inverse of mole. So we get 6.021476 into 10 to the power of 23 per mole is nothing but the Avogadro's number. So therefore, number of moles contained in a particular substance can be given by how many particles are there. When we divide the number of particles with a given Avogadro number, you will get number of moles that are present in a given substance. In addition to fundamental quantities, we have something called as supplementary quantities. Okay, so we also have supplementary quantities, and one of the supplementary quantities is plane angle. The second supplementary quantity is solid angle. Okay, so let us study about plane angle first. Plane angle is nothing but, it is an angle. Suppose this is a circle. Suppose there is a circle. Alright. From the circle, from this origin point, center point, I just take a radius r. Alright. Now, this radius subtends a small angle here, that is d theta, and an arc is here that is called as ds. Correct? So the angle subtended at the center of the circle, at the angle that is subtended at the center of the circle by an arc, and the arc is nothing but it is length to the radius of the circle. Okay, the arc whatever is there is same as what the radius is. So such type is called as a plane angle. Now plane angle is represented by d theta. D theta is nothing but ds divided by r. What is ds? ds is nothing but the arc length. Okay, the arc length is same as the length of the radius. So therefore, arc length divided by the radius of the circle is nothing but plane angle. And the unit given for the plane angle is radian. Plane angle is denoted by t theta. and ds is called as the length of the arc, r is called as its radius. Now let us know what do you mean by solid angle. Yes children, now we will study something about supplementary angle, and that is the solid angle, the second supplementary angle, that is solid angle. Now I have a cone with me here, right? Basically it is a circle, okay, and I have just rotated it to form a cone. All right, yes, I'm sure that most of you have seen a cone, how it looks like, right? So this is a cone, right? So this is basically a cone that I have got it from. Now this cone is nothing but hollow cone, right? Here there is an angle. Now suppose if for this cone, okay, let me just mark, this is a cone, right? Now if I have to mark certain angle here, cone is a three-dimensional figure, here I have marked an angle, okay? So you see, this angle is nothing but d omega. This angle is called a solid angle in a three-dimensional space. Now, so therefore I can say the surface which is equal in the area of the sphere, okay, the surface which is equal, the surface, there is a surface, right? So this entire surface is the 3D surface. It is equal to what? If I open this, it becomes a sphere. Its area is equal to that of a sphere. Now can you see here children? This is exactly how solid angle looks like. Yes, so this and this together, and this area is completely called as dA. From here to here, this is dA. From here to here, this point to this point. All right. So dA divided by r square is nothing but what? Solid angle. The entire area, when I opened this cone, I got one surface, two surface. So this is the entire area, the surface area enclosed, divided by the radius from here to here, the radius enclosed. Okay. So d omega is equal to dA by r square. I hope this is clear to you. So these are nothing but 7 fundamental quantities plus 2 supplementary quantities. Now let us get going for the next. Let's start. We have different types of units in physics, okay? We have, this mass, length and time. We categorize under 4 systems. First system is called as FPS system. It is called as a British engineering system, where F symbolizes foot for length, P symbolizes pound for mass, and S symbolizes second for time. Then we have CGS system, which says C for centimeter, G for gram, and S for second. Centimeter for length, gram for mass, and second for time. Then we have something called as MKS system. M for meter, K for kilometers, and S for second. So meter for length, kilogram for mass, and second for time. Then we have something called as SI system. SI, International System of Units. Yes, and SI system is also called as rationalized MKS system. So what is all about this? Let us check out.
What it actually means to measure something. Well, in science, a measurement is considered the assignment of a numerical value to an object's physical property. Measuring physical properties such as length, volume, and density is very common. For example, you might want to know the length of a line, the volume of a sphere, or the density of a liquid. Whenever we take measurements, we also have to assign units to the numerical quantity in order to convey the relative size or magnitude of the property in question. For instance, if I said the length of my shoe was 10, you wouldn't actually know how long my shoe was because there would be no context for what the 10 represents. In fact, this measure would only make sense if the number 10 had a unit of measure to go along with it. So what is a unit of measure? In order to have accurate and reproducible ways to define magnitudes of length, volume, density, etc., scientists have developed various systems of measure. These systems are made up of units of measure, which are basically standardized amounts of various physical quantities. The SI system is the international system of measure used by scientists. It is a very comprehensive system with many units of measure. However, we will only need to cover a few of these units in order to prepare for the T's. The fundamental physical properties you will need to know for the T's are as follows: mass, length, temperature, and time. You can see that for each property there is a mathematical label, which is used in formulas, and the actual name of the corresponding SI unit or measure. Please feel free to pause the video and familiarize yourself with the information on this chart. Notice that the chart refers to these units as base units because they help to define more complex units, which are called derived units. For example, area is a physical property that uses a unit called meters squared. Since meters squared requires the meter in order to be defined, it is considered a derived measure or unit. Let's walk through an example that will illustrate how the meter is actually used to define area in meters squared. If we take a line that is 2 meters in length and then create a square from 4 of these same lines, we can find out the area or two-dimensional space that this square occupies by squaring the length of the original line. We're not going to talk about the math concept of squaring in much detail here, but just know that in essence, we're multiplying a base length measurement by another base length measurement, which is 2 meters times 2 meters. And this results in an entirely new derived unit called meters squared. Now that we understand a little bit about derived units, let's take a look at some important ones that you will need to know for the T's. By looking at this chart, you might have noticed that things like mass per unit volume and meters per second are also considered units of measure, just like the liter or the Newton. The only difference is that some measures, such as liters and newtons, have a unique unit name, while other measures have unit names based on their mathematical formula. Also note that some derived units require other derived units in order to be defined, which is the case with both density and pressure. Now don't worry if you're a little confused about these measurements and what they're used for. We will discuss them in more detail.
Yes, children. Now, SI derived quantities. Okay, so just as how we have derived our base quantities, now let us know about derived quantities. How are SI units converted into our base units? Alright, now first SI unit of derived quantity is frequency. Frequency is nothing but hertz, right? So hertz is nothing but frequency, that is nothing but 1 by time period. We know that hertz is not a base quantity, right? So it's a derived quantity. Derived from where? Second. So therefore frequency is equal to 1 by time or 1 by second or per second. So therefore the frequency has a base derived quantity as per second. Now similarly force. The SI unit of force is Newton. Symbol is N. Now similarly, expression in terms of base units. Base unit means mass in terms of kg, then time in terms of second, then length in terms of meter, temperature in terms of Kelvin, luminous intensity in terms of candela, and also amount of substance in terms of mole, N. Alright, so all of these I have to derive them all. See, SI unit is Newton. Is it in meter, kg or all? No. So I have to derive this into that form. Alright, so how do I do this? We know that force is equal to mass into acceleration. Mass is nothing but kg. Acceleration is meter per second square. So therefore force or Newton is nothing but kg meter per second square. Alright, now third one is pressure. What is pressure? Pressure is nothing but force applied to that particular area. I am giving a pressure, right? So I am applying a force to this area. So force applied to this particular area is nothing but pressure. So therefore, SI unit of pressure is Pascal and the symbol that we use is PA. Okay, Pascal and PA. Expression in terms of base unit. So how am I expressing this in terms of base unit is P is equal to F by A. We know that force is equal to kg meter per second square. We have derived earlier, divided by the area. Area is meter square. So kg per meter second square per second square. So therefore I can write pressure is nothing but kg per meter per second square or Newton per second. Yes, children. Next derived quantity is energy, work or quantity of heat. Alright, the SI unit for energy or work done or quantity of heat is nothing but joule, right? So if there is if a quantity moves at a certain distance when we apply a force, then we say that work is done. Work is done is nothing but what? Heat, right? That means joules. So therefore we can say that joule is nothing but force into distance. Force is nothing but what, children? We have derived earlier, that is kg meter per second square. Distance is meters. So kg, write as it is, meter into meter, meter square per second square. So therefore we write that work done is nothing but Newton meter, or joule is equal to Newton meter. Work done or joule have the same unit. Then coming further, we have something called as power or radiant flux. What is power or radiant flux? Consumption of energy in that particular time is called as power. And power is nothing but consumption of energy in joule divided by time taken. So we know that joule is nothing but kg meter per second square into meter square, right? So kg meter square per second square into per second, that is time, right? So 1 divided by s, or per second. So it will become s raised to minus 3 into s raised to minus 1 gives me s raised to minus 3. So kg meter square per second cube is the answer. Then we have something called as electric charge. So what is this electric charge? Electric charge is measured. Okay, charge is nothing but what? The current that flows through it. The charges that flow in a conductor form a current, right? So the charge, electric charge is measured in coulomb. And the SI unit or base unit is nothing but ampere second. Okay, so this is it. Yeah. Yes, children. Now we'll go ahead with electric potential. Okay, electric potential is denoted by V. Electric potential or potential difference, right? So all this is nothing but one itself, potential difference or EMF, electromotive force. Now, what is electric potential? Amount of work energy needed. Suppose this charge Q is here. Alright, suppose there's a charge Q, the amount of work energy needed to move a unit of electric charge from reference point to a specific point in an electric field. Suppose if I'm moving this charge to one from reference point to one point in the electric field, right? So this is called as potential, electric potential, right? Or potential difference, or electric, electromotive force is induced here, right? And the SI unit for electric potential is given by volt, that is V. So K is called as the Coulomb constant, Q is called as the charge, and R is called as distance of separation. Distance of separation between both of them. So therefore, the SI unit of electric potential is volt. Volt is expressed in terms of power divided by current, P by I, right? P by I. P, power is nothing but watt, I is nothing but ampere, right? So therefore, watt is nothing but what, student? Power, which we derived earlier, kg meter square per second cube divided by ampere A. So therefore, bring ampere up, it will become per ampere, A raised to minus 1. So therefore, this is nothing but electric potential in terms of my base quantities. I hope you understood till here. Children, the next concept is nothing but capacitance. What is capacitance? The ability of a circuit, okay, to collect all these charges and place them together. That is called as capacitance, okay. The ability of a circuit to collect all the charges, all the energy from the charges and store them. That is called as capacitance. And capacitance is expressed in terms of farad, okay. What is farad? Coulomb divided by the electric potential, right? So therefore, Coulomb is what, children? Coulomb we express in terms of base unit, that is ampere second, divided by electric potential, that is kg meter square second cube per ampere. Now what I'll do? Now ampere raised to minus 1 is here. So if it will go up, it will become ampere raised to minus 2. Kg is in denominator. If it will come to numerator, it will become per kg. Then meter square, which is in denominator, if it will go up, it will become per meter square. Then there is s here and there is per s raised to minus 3, right? So when it will go up, you will get, yes, children. So it will become s raised to minus 3, s raised to 1. 3 will go up, it will become s raised to 4. So therefore, farad is equal to ampere square per kg per meter square and second raised to 4. I hope you understood till here.